So for those of you who were on the field tour, Teddy mentioned there's some interest in the LiDAR. The backdrop for that title slide is the data that was collected by West Fork the day of that field tour. I didn't put the picture with the cars and people standing around, but they're actually in part of the data. So I'm going to talk about this drone LiDAR, probably more appropriately called unmanned aircraft or uncrewed aircraft LiDAR. Some of the operators get a little touchy about the drone word. There's too many connotations of military applications and that kind of thing. So LiDAR in general, we're dealing with firing laser pulses from an aircraft and then measuring the time it takes for that pulse to travel to an object and reflect back to the aircraft. Once we know the position of the aircraft from a GPS unit and we know kind of how that aircraft is oriented, we can calculate where that laser is pointed and get an XYZ point for everything the laser hits. We combine that with the scanning systems where the laser's actually swept back and forth, or in this case, all around. And we get a whole bunch of data generated in a fairly short order of time. So what these things look like, the specifics of this sensor probably are not as important, but when we're dealing with a drone-based system, they're small, they're lightweight, everything has a trade-off. If the system's heavy, they can't fly as long, so it takes more battery charges to get up in the air and do work. And one of the downsides with these smaller systems is they tend to have a somewhat short range. The system that was used for the data that I'll be showing today, max range is listed as 100 meters, but in reality, it's probably more in the 80-meter range. Unfortunately, our trees in the Northwest are tall, and we have steep topography. So you put all those things together, and sometimes it's a real challenge to stay out of the trees. Pilots don't like to get close to trees. A big investment that they're dealing with, and they don't want to touch a tree. This particular system is not your typical Costco brand drone. This is a DJI Matrice Pro. It's a good size system, about 1.5 meters across. It'll lift 10 pounds, flies for 15 to 20 minutes, maybe stretched out to 25. They can cover a lot of ground in that short period of time. When we're talking about how they acquire the data, I always like to think of it as you're mowing the lawn. You're going back and forth across your lawn. And in this case, they go back and forth north-south, and then they flip it 90 degrees and go back and forth east-west. They're overlapping each swath by about 70 to 80%. The point density in this data is, exceptionally high. We're dealing with 40 to 60 pulses per square meter. And the system can get up to 3 returns or 3 measurements for each shot of the laser. So that translates into a single swath with about 40 to 160 points per square meter. When we aggregate all those crisscrossing lines, we end up something on the order of 1,000 shots per square meter, or about 1,500 points per square meter. So extremely high dense data. A lot of details captured, and I'll show some of that, some examples, and then things that really aren't captured as well. So the individual swaths, in this case, they're about 145 meters wide, and that's flying about 70 to 80 meters above the ground. The instrument is trimmed to see about 120 degrees, wide, so 60 degrees on each side of the instrument. And that becomes kind of important because when we see the center of the swath where the laser's firing more or less straight down, or maybe kind of behind the aircraft, the way this one's configured, we see a lot of hits off the tree crowns, but we also see penetration through small gaps in the canopy to hit the ground. So it's not, we see a pretty decent mix. As we get to the edge of those flight lines where we're looking at a 60-degree angle, shooting that laser more or less to the side, we start to see a lot more hits on stems. This one, the aircraft was probably to the right of that little image plate. So we see a lot of stems. We see one side of the crown represented in the data because it's on the edge of the flight line. So on the left side, we see the right side of the trees, and the right side, we see the left side, whatever. But when we put it all together, when we get these multiple flight lines, multiple swaths covering the same piece of ground, we see a really good blend of points in the canopy, points on the ground, points on stems. We see representation of understory vegetation if it's present. And kind of the ability to see deeper into the canopy really depends on what the overstory looks like. So a really dense, thick overstory, we'll see a lot less data down close to the ground. When we think about traditional LiDAR, and that would be LiDAR data that's like been collected by DNR for large areas over the state, over big portions of the state, we're typically dealing in the 8 pulses per square meter range, and that nets us about 13 to 15 to 20 pulses or points per square meter with multiple return systems. Aggregated for the drone data, we're looking at more than 1,000 points per square meter. So just that comparison on the left is the kind of traditional airborne LiDAR, really designed to get the ground, do a good job on the ground model. And the right is the drone-based data. A lot of detail in the canopy with the drone data that is just not present in the traditional airborne data. That detail starts to become important when we want to think about monitoring what happens on the ground during treatments or other disturbances. So some of the basic questions for the drone data, you know, kind of the first obvious thing is, can you come up with something that tells you about stand structure? Can you cleanly and accurately identify individual trees? What can you figure out about each tree? Can you figure out some attributes that are useful? And a big question for me, because I'm a tool developer and kind of big part of my work, is do the same algorithms work for traditional, or that were developed for traditional LiDAR, work for this really high density data? They're really the same, this kind of normal airborne data and the drone data, but the density introduces some interesting twists into the analysis. The UAS captures really high level of detail, but in some cases it may be more detailed than you really want or need. And little things that we take for granted, like, yeah, there's wind most days on the coastal areas in the Northwest. Trees move. You know, if you've ever tried to watch the top of a tree through binoculars, it's absolutely amazing how much trees just gently sway with almost no apparent breeze. Can be a challenge. So when we think about forest structure, kind of a classic way to look at it, this is some work from Bob Van Pelt at the University of Washington. I'm envious of people who have great artistic ability. I don't draw worth a hoot. So, you know, triangles and sticks and crayons are my level of artistic rendition. But these images have been kind of the classic for forest structure. You know, we have dead trees, we have dying trees, old snags, material in the ground, all those kinds of details that we think about when we think of stand structure. Well, my new poster child for the drone data is a profile through a section of these point clouds, and we see very similar information. We see standing trees for sure. We see live, vigorous crowns. We see some crowns that are a little less vigorous. A lot of branch structure down lower in the canopy, which we just don't see in kind of broad area LiDAR data. If there are gaps, we see understory vegetation. Not surprising, we get some light down into the canopy, we get some growth. If there were down logs, I don't actually see any in the image that's there that are very clear. We see down logs on the ground to some extent. And I mentioned, you know, if we have dense overstory canopy, we don't see as much down deep in the canopy. So I mentioned the individual tree questions. So if we think of a surface that's been dropped over the top of all those points, and each of those peaks now is supported by a bunch of points, we can delineate individual trees. So these are kind of polygons for the tree crowns. And that allows us to cut out the points for a single tree. Once we have those points, height's pretty obvious. The top point, the highest point in the tree, we just subtract the point on the ground below that and we get a tree height. I'll almost guarantee with this data, we can accurately measure heights better with the drone data than we can on the ground. Challenging in dense Douglas fir canopies to see the tops of trees well enough to measure really accurate heights. Other attributes, crown base height is a pretty straightforward determination. We can come up with some ideas for what's the crown footprint, you know, a north, south, east, west distance or width. We can compute the area of a polygon that represents a tree crown. What's the radius of the equivalent circle to get a crown width? Variety of different ways to do that. All of them sort of give us an idea of vigor on that tree. Stem diameter is a little more of a challenge. While we would like to think that with 1,000 points per square meter, we could directly measure stem diameters, we just can't. The data doesn't support that level of detail. So we're stuck kind of predicting diameters, and we have, you know, equations for height to diameter relationships. Some are more regional in nature, so Washington, Oregon scale, but there are specific equations for the Olympic Peninsula. Pulling equations out of the forest vegetation simulator or other growth models is an option. One of the things that's critical in doing that is species. So we look at the drone data for individual trees, and for some species, differences in the shape of the crown are really obvious. The metrics that we typically calculate from these point clouds capture some of those differences. So one of the current focuses with the undergraduate student and some work that I'm doing is looking at the upper 3 meters of the crown to decide or figure out if there's machine learning methods that can help us figure out what species it is. So just for comparison, the upper 3 meters of a Douglas fir tree and a Western hemlock look very different. The droopy leader on a hemlock is obvious in nearly all the trees we can identify. So kind of preliminary results on this, we're using machine learning. It looks like we can separate Doug fir and hemlock about 85% of the time, maybe a little better than that. There's a potential for imagery to come into this. You know, we have statewide imagery that's collected every 2 years through the National Agricultural Imagery Program, NAEP. Kind of coarse resolution, especially compared to this drone data, but certainly useful. UAS imagery is also a possibility. It's kind of hard to imagine that you could get any more detailed with an image in terms of being able to recognize species or identify condition of individual trees. This is an option with West Fork can actually fly the imagery as well. We did not collect imagery with the drone data, the drone LiDAR that it's been acquired to date, but that may be an option this summer to look at some possible imagery. So we think of these things, you know, it's kind of like traditional LiDAR, but it's a little different. There's some range limitations. The sensor's a little noisy, you know, and it may not really be that it's that much noisier than a traditional LiDAR system, but we have a really tiny laser beam. The diameter of that beam is really small, so any noise tends to show up maybe a little more. Tree movement, so wind can give us ghosting with those multiple passes over trees. So kind of my conclusion so far has been, you know, this increased detail is really good, this high density, but at the same time, there's some issues that happen because of this amount of detail. My simple example is if I look at a canopy surface model that's kind of colored by height, with the red areas are taller places, taller trees. This has been smooth. It's 50 centimeter resolution, so half meter resolution. It's been averaged on a 3x3 window. The drone data certainly supports much higher resolution products. So this is a 10 centimeter canopy surface. Again, smoothed a little bit. And, you know, while it's kind of neat to see every branchlet and every branch kind of represented in an upper canopy surface, if I were trying to identify individual trees with the image on the right, every algorithm that's been developed to work with a canopy height model would fail. It would tell us there were thousands of trees out there instead of hundreds. So that detail is not always a good thing. So when we think about our treatments, treatments are dealing with a variety of features, right? opening and clumps, retention patterns, planting of different species, different densities, non-timber plants. So we're going to put some things that are not trees out there. What kind of coarse woody debris treatments are there? How much slash is retained? Do we want to put the slash in certain places? All of those features of the treatments are important to capture. When we think about our traditional kind of breakout, the top two of those things are really overstory features, picked up really well with the drone data. The lower three of those, the latter three, are more down deeper in the canopy. And as I said, if you have a dense overstory, you get a lot less data down deeper in the canopy, including the ground. We get fewer points on the ground than we might like under a dense closed canopy stand. When we think about field plots, I know early on this morning, Bernard mentioned that there are field plots that have been installed and measured in the T3 areas. Some more are being measured this summer. Typically, those plots are pretty small. There aren't very many of them because they're expensive and they take a lot of time to measure. And they're best for capturing like general conditions. You know, what's the density of trees before and after a treatment? How much volume is out there? How much defect maybe is out there? Although I don't think we're collecting defect on the plots that are being measured. But they don't capture things wall to wall for a particular treatment unit. And when you think about using field plots to do that kind of monitoring, we are seeing everything or trying to get a good enough sample that you can make educated statements about what's there or what's not there. It's really hard to put in enough plots and put them in the right places to capture all the changes that can happen on the ground. You know, even with our best planning, and we've talked about logging folks coming in, things change on the ground. If we're not designating specific skyline corridors for cable operations, the operator may move things around a little bit to better accommodate their crews and their equipment. So we can't put plots in that necessarily are going to capture pre and post conditions, you know, condition changes as we do the treatments. So I've taken one treatment area, and this is one of the westernmost areas designated in the DZ set, for whatever that tells anybody. This is an area that's been thinned probably within the last 15 years, maybe 20 years. So it shows some treatment effects in the overall pattern of the data that was collected for it. So this has drone data over the treatment unit. If we look at the canopy height surface, so this is the point cloud, kind of had a surface fit to it, and then we're just coloring it by height. We can very clearly see the thinning corridors, or the skyline corridors from the thinning operation. We can see some gaps. We can see some clumps of taller trees, those red ones, and some areas that are more generally lower, smaller, shorter trees. Having that canopy height surface, we can calculate how much gap there is. And we can calculate that on various thresholds. So we can say below 2 meters, how much opening is there? Areas that are below 8 meters, how much opening? So this image down here is 14.8% of the area has vegetation 8 meters and below. That kind of analysis is really straightforward with the LiDAR data. When we get to the individual tree level, well, if we can isolate individual trees in the upper canopy and basically map every stem on the treatment area, pre and post data collections will tell us which trees were removed, potentially the exact volume that was removed. Well, maybe not exact, a good estimate of volume, but more importantly, the patterns that we generate. You know, if we're trying to deal with variable patch sizes, variable clump sizes, we can do a good job of quantifying those from this individual tree data. We can also start to look at the distribution of heights for those individual trees that were detected. And then through prediction, we can look at the distribution of diameters. Again, we're dealing here with overstory trees, not getting into the understory, mid-story level, you know, trees. So the future kind of looks good, I think. In general, the UAS data is very similar to traditional LiDAR, but it does have differences. The existing analysis methods and software work pretty well. There's room for a lot of new development. That high density offers a lot of possibilities for getting additional information out of these data. So the potential is a monitoring tool. You think about it, it's not cheap. You know, you're putting a person on the ground with an expensive piece of hardware and asking them to fly 20 acres, 25 acres. They have to get there. They have to figure out the flight pattern. They have to do some testing to make sure they're not going to hit any trees. But fairly short notice, they can be out and fly an area. So it's really well suited to project level analysis. And by project level, I'm mainly thinking, you know, relatively small areas. We're not looking at a 40,000 acre watershed, but we're looking at a collection of treatment areas that maybe aggregate up to 150 to 200 acres. The individual tree detail is pretty good. The overstory for sure. We get overstory trees pretty clean. Maybe some mid-story trees, but the more overlapping, intermingling there is of crowns, the harder it is to tease those apart. General structure information and definitely spatial patterns are pretty easy to generate. So maybe the general change detection and treatment effectiveness are things that can be addressed with pre and post data. And then the final thing to wrap up with is, you know, what are the new questions? We kind of have a bird's eye view of an area with data we've never really had access to before. There's a lot of detail there, but like I said, there's some challenges in teasing information out of that detail, but the promise is really good.